Good morning, students. You know what the best thing about AP Physics Kids is? I don't even have to be here, and you guys can still dominate the lab. Isn't that great? So, we're going to start talking about springs, and here's the reason. Let's set some context. The reason is springs apply conservative forces. And let that sink in. Conservative forces, all right? You know so far of a single conservative force, a force that when it acts on a system or part of a system can conserve mechanical energy within that system. And that force is, yell it, congratulations, yes, it's gravity. Gravity is a conservative force. Well, springs, what we call ideal springs, also exert what are called conservative forces. Right? So you know when we talk about maybe a bow and arrow sort of situation. Well, a bow and arrow is kind of like a spring. The bending of the bow itself acts like a spring, but we're going to deal today with nice coily linear springs. And a spring is nothing a whole lot more than a piece of wire that's just bent around, in a nice coily shape. And then there's some treatment, some heat treatment that makes that shape sort of semi-permanent. Okay, so what you have likely in front of you, you better, is a spring hanging from a string attached to the ceiling. And what you can do by manipulating it with your hands is make it apply different forces. And that's important. You can make the spring apply different forces. Okay, you can make the spring pull a little bit or pull a lot. So monkey around for a couple of, a minute or so, and then describe how you made that happen. I will give you 90 seconds. Go. Yeah, just let this play. Kids are doing stuff. So hopefully you've been able to, that might be short of 90 seconds, but hopefully you've been able to describe in words how you made the spring apply different forces. And, well, spoiler alert, the answer to that is by stretching the spring to different lengths. Yeah? So you should qualitatively be able to tell that the more you stretch a spring, the harder the spring pulls. You can feel that. Right? So you in this lab are going to investigate a couple of questions. One, on what factors does the force that a spring applies depend? Well, you already know one. And the bigger question here is what mathematical relationship exists between what we'll call F spring and these factors. Actually, you're really going to only investigate one of the factors because the spring you use is going to be, well, the same spring you use. And that spring has a certain constant property that's based on how the spring is manufactured. All right, and that's going to remain a constant. Number two is how much force would the spring apply if you stretched it a whole meter? Well, guess what? A lot of these little dinky springs, if you were to stretch them a whole meter, they won't recover. All right, so don't do that. If your spring gets permanently deformed, it means you are not exhibiting good lab practice, and that is something that is well, it's just something you're not going to do. All right, so these springs are going to look exactly like they looked when I left them the next time I see you. So, but even with that said, you can't stretch them a whole meter, but based on the data you collect, you're going to be able to tell me, you're going to be able to extrapolate and tell me, well, if it was stretched a whole meter, here's what would happen. And specifically, here's how much force the spring would apply. Now, here's what you're going to do. Notice we have the springs hanging from the ceiling. And the nice thing about that is we can hang things from the spring. Okay? I'm going to pause and let you read this. It's annoying when people read things to you, so I'm going to pause and let you read this. I'll be back in a bit. Go ahead. All right, I read it slowly. Hopefully you read it as well. So you're going to draw in this area here. I'm going to take it to a different page. We're going to draw something called a free body diagram, and we're going to identify the forces that are acting on our object, right? Now, the nice thing about free body diagrams is you don't have to be an artist, all right? We don't have to draw, you know, like something special in terms of you know, we don't have to draw a special fancy, you know, what's the word I'm looking for? You don't have to draw anything artistically. What you have to be able to do is just say, well, here's an object, right? You know, we can just say, yep, object. It's you're going to hang masses from this spring. So here's the mass. All right, so what forces act on the mass? Well, one of them that pulls straight down is gravity, the force that Earth's gravitational field exerts on this object. And the other one is, well, the spring. If you want to write the whole word spring, you can. I put Fs. All right, the spring pulls up, gravity pulls down. All right, and specifically because this object is at rest, or what we call in equilibrium, it tells us something about these two forces. Can you guess what it is? It tells us in equilibrium, F spring equals Fg. Those two forces are equal and opposite. Guess what? They add up to 0. That's what this means. It means the net force, the total of all the forces, is 0. And sometimes when objects are in equilibrium, they will be at rest. So here's the deal. When we try to make a measurement of the spring force, well, that by itself is kind of maybe tricky to do, except we can make what's called an indirect measurement. We can make an indirect measurement and say, well, since I know one force, and since I know something and something are equal, by measuring one thing, I'm actually measuring something else. We want to measure the spring force. That's kind of hard to do directly, but what's easier to do directly is to measure this. We can measure gravitational force, or we can calculate it really. And here's how we do that. All right, here's what you know already. Earth's gravitational field strength in this room is 9.8 newtons per kilogram. Usually we write that as 9.8 newtons per kilogram, but I wrote it like this, same thing, 9.8 newtons per kilogram. So G, that says, is a measure of, well, this 9.8 newtons is a gravitational force per unit mass placed in the field. So G, we can write as force over mass. And that means if we want to know what something weighs, what force Earth's gravitational field exerts on it, we just rearrange this equation and we get that something's weight is m times g. This is a subscript. This is the 9.8 newtons per kilogram. So for example, if we had a mass of 200 grams and we want to know what that weighs, well, we do m times g, or, well, I got to change it to kilograms times 9.8 newtons per kilogram. And notice our kilograms divide away, and we're left with a force, well, a weight. We're left with a weight in newtons, and 0.2 times 9.8 happens to be this, hey, it happens to be that this thing weighs, that's to 1.96 newtons. And guess what? If you were to hang a 200-gram mass from this spring, right, here's the mass. Well, this force is 1.96 newtons. Guess what? So is this. So by measuring the weight, we are indirectly measuring the force that the spring applies. Okay? Pause. Pause. Okay, on to the back. Here's a big piece of terminology, a major idea to keep in mind. I will let you read this. Okay, I'm not going to read it to you, but it's super important. And when you record data, you need to record something. You need to record this quantity that we're talking about in this major idea. All right. So again, we're sort of the place we started is the question is how much force do springs apply? And you know, like most questions in physics, that's not a simple question. And your answer should, you know, you should take some things into consideration when you form an answer. Here are some things to read through before you start. You don't have to do it right now, but read. And by the end, you ought to be able to answer or fill in these blanks, right? You're going to collect some data, right? You're going to collect enough data, quote, enough data that you can feel confident about a conclusion. You're going to make a data table. You're going to make a graph by hand. There's graph paper that will be provided for you. You have to use your graph to calculate something. Guess what? The answer to one of the big two questions on the front comes from a calculation of something from your graph. And, oh, big one here is don't ruin the springs. All right, your substitute has been instructed to make a special note of any groups that ruin springs. So don't do that. And what else? What else? Oh yeah, graphs. When you make a graph in physics, I don't know where you learned it, but some people taught you at some point in your studies that when you make a graph, you should connect the dots. Don't connect the dots. Do not connect the dots. Graphs, for us in physics, are ways to identify general trends in data. General trends. Do not connect the dots in a graph. Instead, if you think you have identified a general trend, you can try to draw that general trend. Okay? If you think you see a predictable curve, then try to sketch that curve. If you think your data is a straight line, use a ruler and draw a line of best fit. Okay, folks? Okay. The pride I feel in you for not even being here and knowing that you will crush this lab, the pride is palpable. All right, so do your best. Enjoy. I'll see you soon. I'm done. I'm almost done. Bye. It's over.